really know what that means. Truly. Does not mean line, believe it or not. So, is that linear? Wait a little bit, kind of his opinion change. This is linear because all the powers of the variables are first power. That's the true definition of linear. All the variables are to the first power. So it's not quadratic, it's not that. It's a linear function in three variables. So it's all of them to the first power. So when we say linear approximation in Calc 1, we actually mean a line. When we say linear approximation in the variable calculus, we mean normally a plane. An approximation to a surface, right? So when we find that tangent plane, the points that are on the plane that are near the point should be approximations to the actual outputs. That's the idea, right? So the funny thing is, the equation of a tangent plane that we found, and in fact, let me kind of build up to this. If I had something in this form here, so remember, if I have this leads us to this here idea here. For the tangent plane, right? Now what would change if I had it like this? If you do this, and I really want you guys to understand this. This is kind of, in my opinion, this is kind of silly. This is this. Just they solve for z. Right? So it really shouldn't change. This is just a special case of this. The formula should still be true. What's fz going to be, though? You do it? So if you solve it and make it look more like this, don't you get z minus f of xy equals 0? What's fz? It's 1, yes. Now what are you guys worried about? Are you worried there's some z in here? Can there be a z in here? Because it says a function of x and y. There can't be a z in there. So what's fz? 1. Right? And then what's fx going to be? It's a little weird, I agree, but it's just, the only thing with x in it is little f, so fx is going to be little fx. Right? And what's fy? Little fy. How you guys doing? Are you with me so far? I mean, this is just a special case. If I make the coefficient of z 1, then of course fz is going to be 1. Ooh. Put it in that form, and then I can attack it the same way. So the book makes a big deal out of these two different representations. Personally, I hate it when they do that because it's the same stupid thing, right? I can attack this the same way I attack this. I have to look at it like different situations. So what I end up with here is I get fx, x minus x naught, fy, y minus y. Oops, I gotta be careful here. Looking back at this, what one little thing I messed up here? Anybody see? I love when I make this. Yeah, these are both negative, right? Cool, thank you. So I get negative, negative, and I can take care of that real easy, but negative, negative, plus 1 times z minus z naught equals 0. So it's the same stupid thing. And then if you solve for z, you'll get fx, x minus x naught, plus fy, y minus y naught, plus z naught. Now, what's going on in the background, the thing I'm really not that careful about, and I desperately hope you guys understand, to get a tangent plane, I have to be told what? I can't just get a tangent plane to a surface. I have to be told at what point, exactly. So each of these are evaluated at that point, correct? Each of these are going to be evaluated at the point that I'm interested in. We did that earlier. I've got to plug the point into this to see what the actual number is. So in the book you'll see this, they write it like this. Because what will you get when you plug a, b into the function? You'll get the output. You'll get z, right? So this is really the same as this. Just if you look in your book, they make it seem like it's two different things. They're not two different things. It's the same thing. Okay. The funny thing is, like I was saying earlier, for a linear approximation, it's just that. A linear approximation. So what do I want a linear approximation to do? I want to create a function where the variables are all to at most the first power, if not absent, right, to the 0 power. So then it's easier to plug points in, but it approximates what the original function would have done. Correct? Isn't that what I want a linear approximation to do? I want to get an easier equation that does the same thing that the harder thing does. And if you remember Calc 2, you sort of do that with, you sort of do something similar with, I know saying this is going to bring back bad memories, but Taylor polynomials? Come on, man. But this is even better. Why is this nice? Because it's easy as hell to get the freaking equation for a tangent plane. And I'm only dealing with first powers. Taylor polynomials can go up forever power, right? But it's the same idea. I'm trying to get a polynomial, in that case a polynomial function that approximates something possibly uglier. In this case, I just want a linear function that approximates something uglier, right? So for example, if I have, oh, let's see, here's a good example. Well, this is nice for remembering our derivative rules. So if I have this function, that's a 5, which this is definitely 5. So let's say I want to find the linear approximation at the point -1, 2, 1. So to do that, I want to use this form that we just talked about. Like z equals f x, x minus x naught, f y, y minus y naught, plus z naught. The book will say f of a, b. Whoop-de-doo. I just want z naught. I want the value of z at that point, right? What is the value of z at the point? 1. It's 1. That's awesome. That's why I like to look at z naught. It's easy. It's just the z piece of the point I'm looking at, right? What is fx? Yeah, to do that, you can do, this isn't really quotient rule, right? You guys see that? Because the top is just a constant. I would definitely write this like this. Please do God, don't make it 5x to the -2, y to -2, right? Gotta raise the whole thing up, so I'll need -1 power. So yeah, the negative comes down, -5 times x squared plus y squared to -2. Good, and this is fx, so it'll be just 2x. So just to make that a little prettier, -10x over x squared plus y squared. Now considering how symmetric this function is, are you guys cool when I say that? It's symmetric, x and y is symmetric, it doesn't care which one. What's fy going to be?
Why is it square on the bottom?
Oh yeah, thank you, squared. What's fy going to be?
Same thing, they're going to have a -10y.
I love it. Yeah, -10y. Awesome. Squared. So what's fx at the point and what's fy at the point? Just get fx will be 10 over 25. So 2/5. And fy will be where am I at? Oh yeah, that's right. So -20. So negative? Yeah. Over over 25 again, negative 4/5. So just putting it all together, I get z equals 2/5 times x minus
Plus 1.
good. So minus negative 1, so plus 1 minus 4/5 times y minus 2 plus 1. And then you can, get that to be better. So when can I use this? Thankfully, we're not going to get into that. I think you remember doing possibly some, how big of an area can you put something in and be within so much? Your error, how far off you want to be? Let's not do all that crap. But if I use a point that's near this point, that should be good enough. Approximation, possibly, right? So if I put in there negative 0.95, 1.98, 0.99 or something, I can just throw it in there and get an approximation, right? I wouldn't get that, but just plug in an x and y and see what the z would be. Should be a good approximation. All right, guys? I'm not going to make a big deal out of that, because it's beyond what we've already done, because it's the same thing as before, and it's not really used terribly much, to be honest. Yeah.
So that's a plane, right? The equation of the plane.
Beautiful, I like it. Right? This is an equation of a plane. Like we said before, we don't normally call it, a plane is not a line, but a plane in some sense is linear, because the function for a plane has only to the first powers on its variables.
Yeah.
Good. Okay, cool, awesome. So that was the last little piece of 12.7. So we're going to look a little bit at 12.8.
So the point is the x naught and the y naught.
Yeah, the point that we're
That's the naught.
at the point, at some point I gotta be given that. Sort of like, I don't want to bring up a Spencer Taylor polynomial, but you always have to do it around. Same idea. So, let me, I wish I would have kept that up there, but remember that one we just looked at a second ago? That was the, oh, that's beautiful. That was sort of like the ghost. What would you say is special about that point right there? Good, right? That's the, in fact, it's the local maximum, as it turns out, is definitely the absolute maximum, right? So that's what the next section is all about. And the monster awesome thing we saw is, we saw like a little preview of that from a problem in an earlier homework section where somebody did it in a different way and saw that it came out with the same answer. There are a couple things you have to be careful about, but essentially it should be something about taking derivatives, just like it used to be. Somehow the maxes and mins should be where the derivatives are 0 or undefined. I like it. So let me say a couple things here, and let's see if you pick up on the logic. 1.
So this whole base.
Oh, wait, it's 12. If there's a local max or min at AB, right, then little disclaimer if they exist. Just the cover answer what we just said. If it's undefined, it could be there too. Now notice how people always get confused, and you might remember, I mean, what was the whole point of calling something a critical point? For example, when we do the second derivative. When do you actually call it an inflection point? Only after you check what? It better change, right? And you can't call something a max or a min unless it actually is going up and then coming back down. It can't go, oh, I tricked you, right? So the same thing happens, of course, in 3 dimensions. In fact, it can happen in a lot more ways. correct? Because I have all these other directions I can go in now. So, but the same idea holds. If the max or min is there, then this must be true if they exist. Not the other way around. If this is true, it does not mean necessarily there's a max or a min. This is the old fallacy of the inverse. I don't know if any of you guys have ever taken a logic class, but you can't turn that bad boy around. Secondly, here's the one that's a little more new. If a tangent plane exists at a local max or a min, I'll just say a local extremum. Extremum. If the tangent plane exists at a local extremum, then it will be what? What do you think will be true? Looking back at this picture here, what do you think must be true about a tangent plane at the location of an extremum? Sort of like what's true about the tangent line where there's an extremum. Yeah, it's got to be a slope of 0, which means what kind of a line, which means what kind of a plane. Horizontal. So it's got to be, then it will be horizontal. Again, the inverse is not true necessarily. If you have a horizontal tangent plane somewhere, does that mean that's an extremum? No, it could be one of those fake outs, right? How are we doing so far? All right, like it. So this is all sounding the same as good old Calc 1. So where does it change? Well, it changes pretty quickly, actually. It gets a little bit freaky. Before I get into the freakiness, though, I want to define something. Critical points. Let's make a formal definition of critical point. And let me see if you guys understand this point. An interior point of the domain of some function f is a critical point is if two things. Yep. Or, let me say this, at that point, or fx and or fy undefined at that point. So the nice thing is that's still the same. How do you locate your possible extrema? You find where the derivatives are 0. In this case, the partial derivatives, right? And possibly where it's undefined, if there's anywhere where it's undefined. Okay, how are we doing so far? Thank God for that. We have our partial derivatives. They better act like the derivatives we're used to. They're still derivatives. Yeah.
For part 2, what does it say after f of x? What does that word?
Oh, it's trying to be and or. If either one of them are undefined at that point, then you have to include that in your possible list of your list of critical points. Okay, cool. So far, so good. So let's take a little concrete example that looks a lot like the earlier problem. And when you get something really nice like this is when it works really straightforward. But they're all not all nice like this. Can we find the critical points? For this here. So take a minute and see what you can do with that. Try to find the critical points. One thing I want to point out, if you're doing fx or fy, how many functions of x or how many functions of y are there being multiplied up there? How many functions of x are there? Two. How many functions of y are there? Two. I love it. Right? Because in the y case, the x's are all constants. In the x case, the y's are all constants. It's not as bad as it first looks, maybe. So what are you guys getting? The first step on fx, you can take the derivative of him, and we'll leave these guys alone, right? Plus leave this guy alone, derivative of this one. And then if you factor a little bit, you guys might have done this a little differently, I don't know. Gotcha. You get y plus 3 can come out, and you get x minus 2 plus x, which is 2x minus 2, which is twice x minus 1. I don't know. Did you guys get there? One way or another?
Yeah.
And then fy, much the same, would be, take the first guy, leave the second guy alone, first guy alone, the second guy is just 1. X and an x minus 2 come out, leaving it with y plus 3 plus y, which is 2y plus 3. Okay. So now we have to find all the points that make both of those equations true. We want this to equal 0 and this to equal 0. For that. So you just got to find all the points that make both of these true. It's not that bad.
You said we will do each other.
No, you just do each one individually. So what do we have so far? We got 2y. We got x plus 2, 2y plus 3. So for this first equation, just directly, what do you get? Y equals 0. Y equals negative 3. X equal to 1, right? So if you plug each of these into the second one and solve, see what you get. So for the case for y equals 0, when you plug that into the second one, what do you get? Oh, let's do it like this. What's 2 become? If y is 0, you get 3x times x minus 2, right? How are we doing, right? If you make y equal to 0 and plug it into the second one, so we're doing like a substitution, right? Plug y equal to 0 in the second one, you get 3 times this, and what are your answers there? X equals 0, x equals 2. So I get 2 points, 0, 0, and 2, 0. So those are 2 critical points. Now do the other 2. Keep going. Try this one and try that one and see what you get.
You plug those in the second one.
Yeah, So again, just to make a point of this, I think I wrote this up here earlier, but fx equals fy equals 0 is a condition for a critical point. So they must both equal 0. So I really do have a system of equations. So if I solve one and plug those into the other one, I get my points that work in both, right?
So like I can use in the second equation x equal 2 and x equal negative 3 halves. Oh, y equal negative 3 halves.
So now I want to do y equal negative 3. What's the second equation become? Y equal negative 3, what's the second equation become?
Negative 3x times
3x divided by x minus 3.
Yeah, negative 3 x times x minus 2 is the same thing, right? So you get x equals 0, x equals 2. So what 2 points do you get from that?
0, negative 3.
Good, so you get 0, negative 3, and 2, negative 3. And finally, if x equals 1, 2 becomes 1 times 1 minus 2 is negative 1, so I get tilde negative 1, so I get 2y plus 3 equals 0. Y equals negative 3 halves, so what critical point do I get there? 1, negative 3 halves. So I get 1, 2, 3, 4, 5 critical points. And it should only make sense. I mean, this thing can do a lot of weirdness. I can get an infinite number of critical points very easily, because we've seen stuff like that. They have all these peaks, right?
It's not that bad, it's just
I know. All right, guys.